That's good.
Okay, very good. Good morning, everybody. Welcome to the last lecture. And so today, the topics are to go through a couple examples of the sort of modern applications and things we've been doing at CHESS recently, and how you might want to apply them to your own research. Okay. So let's dive right in. Let me get my pointer. Okay. Like every other lecture this week, we're starting from this point of scattering from a point charge with this simple formula. Again, the acceleration of the point charge creating the radiation field at the detector. The scattering amplitude has all the information, this A, in the cross section, and it's just the scattering amplitude itself is the Fourier transform of the number density of electric charge with units and so on. The same things we've been looking at all week. We calculated the scattering amplitude of a crystal by breaking the crystal into atoms, unit cells. So this is the location of the atom in the unit cell, and then a sum of unit cells to make the crystal. So today, what I want to talk about a little bit is imperfect crystals, the effects of thermal vibrations, of lattice strain, and things like that. And so to do that, I think we talked about this a little bit yesterday, but we look at a generic crystal as just a set of atoms at various positions. So N in this particular case is just indexing the atoms. And at any instant in time, the basic idea is the atom's not sitting at its average position or its equilibrium position, but there's some displacement, U, though, and U is small. And just imagine like a little harmonic oscillator. There's a spring, and so I've got a ball and a spring, and it vibrates back and forth. The zero position is is given by R, and it just vibrates back and forth in a potential well. We get the scattering cross section the usual way. We just put F times E to the IQR, but instead of using R, we use R plus U. We just substitute it in, and there's angular brackets indicating a time average or an ensemble average. To simplify the notation, I have this kind of ugly looking thing up here where I have a vector dotted into the difference of two vectors. And it'll be easier later on to rewrite this thing as the magnitude of Q times the difference of this quantity here, but here U sub Q is the component of U which is parallel to U. So the dot product is already buried in here. The advantage is that this gives me a scalar quantity. I don't have to do vector algebra anymore. That'll help a lot. So UQ is the component of the displacement of the atom, which is parallel to the scattering vector. For a Gaussian distribution of fluctuations, which is a really good approximation for us, the average, assuming that X is Gaussian distribution, is just given by this thing here. And if I assume that this is true, my temporal average immediately factors into three terms. So I have something which this is the average square amplitude of the nth atom vibration. This is the average square atom of the nth atom. This is the correlation between them. I can simplify this whole expression by adding and subtracting 1. And what that allows me to do is put this all back into my original expression. And it breaks into two terms. Up here is the 1. Here is the thing minus 1. And so this is our original expression. If you look back to your notes for the scattering cross section, here's the units. Here is my Fourier transform of the charge. The only difference is that there's an extra little factor here, this Gaussian thing, which just decreases the amplitude of the term. So all of this stuff will still give me all of the Bragg peaks, except that I have to replace my atomic structure factor by the original one times this new decrement. This exponential term is known as the Bywater factor. and in some parts of the literature, you'll show up as e to the minus m. So if you're looking through the literature, that's what the m, just this thing here. But the key idea here, and this is very hard for people to remember this, is that all the Bragg peaks are still delta functions. Okay, that's all that's going on here. You're decreasing the amplitude of the delta functions. You are not broadening them. Okay, and that's a consistent idea. It's going to show up in other contexts. Later on, when we look at this term down below, that will give us the diffuse scattering. But this initial term up here is just the original scattering with, now we have the Bywater factors reducing the intensity. If we now go and look at this term and say, okay, whatever came out of here, in the Bragg peaks, has to go into the diffuse scattering. All those photons go someplace. And so what we're going to do then is expand this exponential. We expect this term to be small. This looks like e to the x. I can expand e to the x as 1 plus x, higher terms. So then I'll have a 1 minus 1, and I just get this argument. If I come down, we'll do that. Here's the 1. Here's the first term expansion. Here's the second term in expansion, and there'll be more. So again, this first term that we've already looked at, is delta function. This is the interesting term here. So let's put in some numbers and think about what would these displacement fields look like. And so one case that we're very interested in is the case of phonons, elastic waves propagating through the crystal. And so we just take a very simple model where a displacement field looks like a traveling wave moving in the g direction with frequency omega. It'll be polarized in some direction and it has some amplitude. There's also a phase term here. So this is just the most general expression for a traveling wave. And then I can sum over all these, whatever my phonon spectrum is, and so on. But I can then calculate this thing here by just substituting this in. And you get kind of a mess. There's, of course, the product of two cosines, because I had two terms here. There's going to be some dot products, and you did dot into Q here, and there's kind of a mess here. But I can simplify it using my cosine forms, and I come out with something down here, which is starting to get simpler. It looks like Q squared, and there's a new cosine dependence here, depending on the distance between my two atoms, and my amplitudes are still running around. It's convenient then to re-exponentiate that and just note that the cosine is just the real part of this thing. So I can, for my algebra, it's going to be easier to go back into the exponential. If I stick that back in, my first order term we were just looking at previously, it becomes like this. If you look at it, it has a very simple structure again. I have my the units up front. This was the Thomson scattering cross section. Here's my Bywater factors. Here's my atomic form factors. Now I get a term which goes like Q squared, where Q is dotted into the direction of the vibration of the phonon. So I can only see phonons where the displacement is along my scattering vector. Then I have a sum over all of my atoms. And instead of Fourier transforming with respect to the scattering vector, I have to add a little bit of wave number, which is, this is the wave number of the phonon. And so I've got a brand new thing here. And this gets added, this is the thermal diffuse scattering part of the cross section. This gets added to my Bragg peak part. So pictorially, what it looks like in reciprocal space is originally I would have had Bragg peaks at integer values of h, k, and l. Bing, out here. But now, and that's the first term, the Bragg scattering, the delta functions. But now my diffuse scattering is going to be located at value q plus g. And so whatever my q value is, there'll be some region out here. So I expect to see diffuse scattering around my Bragg peaks. can get an idea of the amplitude of these peaks by using some very simple arguments. So the average kinetic energy in the sample is just these vibrational energies, u squared times m. So here's a half mv squared, and I have to add this up for every single atom. I can get from my original discussion thinking of these u's as these plane waves. They all had omegas with them. So I can put all this stuff through. So, and I end up with very simple arguments here about that things are going like omega squared. And so I'm proportional to the number of atoms in my sample. So if they all have the same mass, this is the number of them. This is just the amplitudes and their frequencies. So the total energy is, of course, equal to the sum of the kinetic and potential energies. And the average, for a harmonic oscillator, the average energy and the potential energy is equal to the average energy and the kinetic energy. So there's a factor of 2 which jumps in, and which just changes the prefactors out here. But basically, I think I just get a number n now times the energy of a single thing. So this is the average energy of each oscillator. So the total energy is just the sum of all of the energies. But that's okay, because I know by equipartition that the energy of the oscillators is kT. So think back to your chemistry, physics. If I want to be a little more elaborate about it, the phonons or bosons, and I can do the quantum mechanical calculation. So if I'm at low enough temperature, I have to use this. If I go to higher temperature, this expression reduces to this expression. So I'm going to assume that we're at room temperature, well above any quantum effects. And so I'm going to replace these E's by kT. And you get the very simple, pleasing result that these amplitudes go like kT divided by the number of particles. So kT was the energy in the whole thing. This is now the energy per particle. Then the speed of sound and so on coming in the mass, looking the right kind of normalization. So the key thing to remember though is the amplitudes of the vibrations go like kT. Sorry. So if I plug this all back into I now have a closed form expression for the thermal diffuse scattering. It goes like kT, and this is the locations of it. Let's look at some examples. So there's some really beautiful work done. It's almost 20 years ago now. This is let's see if I can remember which side is which. On the left-hand side is data, and on the right-hand side is calculation, simulation. What we're looking at is you take an X-ray beam and you just drive it through a silicon wafer. In one case, it was a silicon 111. In the other case, it's a silicon 100, so wafer. And so on the left-hand side, you can tell it's data because you can see the shadow of the little stick that held the sample and the beam stop. So the sample, you have to imagine the X-ray is going through the sample. And there's a little stick with a beam stop in front of the detector so that the main incident beam doesn't burn a hole in the detector. Martin Holt did this experiment, and it's actually a very beautiful thing. So there's some things to remember. If you look in the center here, this is where Q equals 0. What you see is that there's no thermal diffuse scattering. I should point out there are no Bragg peaks in this picture. This is just the thermal diffuse scattering. We're not on any reciprocal lattice band. We're not at the diffraction condition. This is just the diffuse scattering. And if I go to Q equals 0, there is no scattering. And if you look back at our formula, there's a Q squared in here. So as Q goes to 0, the scattering has to go to 0. So the thermal diffuse scattering is 0 near the origin. But then around each Bragg peak, the thermal diffuse scattering picks up. And so you see enhanced scattering near every Bragg peak. So it looks like Bragg peaks here, but this is really all thermal diffuse scattering. The first thing to note is that the region near the origin is dark. The other thing is that we can only see the transverse modes. So since Q in this particular experiment is perpendicular to the plane we're looking at, right, always scattering sideways, we can only see phonon modes, those which are polarized perpendicular to us. Now, so we're just seeing the transverse phonons. Now, so Q and U have to be in the same direction. Okay, and then near every Bragg peak, we see the enhancement due to the 1 over G squared dependence of the thermal diffuse scattering. So as G gets small, that's the wave number of the phonon. The amplitude goes like 1 over G squared. And so that's what you're seeing here, and here, and here at all the Bragg peaks. So it's actually a really wonderful example of finite, and then you have all this information from here. And so he's got the model on one side and the data on the other. You can see it's really excellent agreement. And we can use this same formalism to study other effects. That there are other things which can create these displacement fields in the crystal. And excuse me, one of them is strain. And so go back to very simple things here. Bragg's law is that lambda is 2d sine theta. I can rewrite that in terms of q's. So q is 4 pi over lambda times sine theta. Remember, q is just 2 pi over d. I can define the strain of a material rather than the displacement field. The intrinsic property is actually strain. So that's the displacement d divided by d minus d naught over d naught. So I just have to normalize out the size of my sample. If I put that into q, I can get a delta q. So just plugging things through here. So q over q naught. Take the difference here. What you find out as I rewrite it in this form is that if I have a strain in my sample, it'll give me a shift in q, which is just given by the strain. So as my peak moves around, I'll get a shift. And that these kinds of shifts are the basis of almost all the physics or the science that's studied by the folks that look at the strains of materials in the structural materials group. For example, Professor Matt Miller's group. This is where they make their living. So there are various ways to do it. There are two components to strain. There's average strain and the inhomogeneous strain. And there's groups at Cornell do a lot of this. The Schuss-Baker's group looking at the average strain. And I don't want to go through all the details here, but you look at these angles psi and phi. And characterize the direction of q. So if you go through the calculation, you'll see that the strain comes out with this formula. You notice all these psi squareds here. If I plot the measured strain versus psi squared to the q position, you can actually pull out these coefficients by doing a psi squared measurement. So here's a couple typical ones where if you plot the measured lattice constants as a function of psi squared, it actually allows you to pull out all of the the homogeneous strain in coefficients, so you can measure these things here. That's just one of the techniques by it. So all we're looking at here is the shifts in the Bragg peaks. Okay, that's all that's going on here. It allows you to recover these values in very simple analysis. On the other hand, if the strain is not homogeneous, so in a homogeneous strain, every single unit cell is distorted the same amount. In the real world, that doesn't have to happen. The different unit cells might be distorted different amounts, and that will give you a line broadening. So we've already seen finite size effects, where if you think back to your notes, we have this equation for sine squared nx over sine squared x. So if I have a finite size sample, I get a peak whose width goes like 1 over the number of that n. And so the delta q, the width of the peak, looks like 2 pi over the size of the sample. Similarly, if I have a strain variation, remember q times e was the motion of q. Well, if there's there's an average value, it could be 0, but if there are fluctuations around that value, so I can get a width to my peak, which looks like the mean square value, square root, and I get the microstrain. This then we'll get a different way of giving me broadenings from strain or from displacements. The total broadening, of course, is the sum of these two, and we can add them in quadrature. So some beautiful examples of the difference between coherent strain, which is the main thing where you can see the interference patterns building up. And this is an example by Chen Shen and Stefan Kitcha, where I actually looked at little pillars of silicon and for their experiment. So if you take a silicon crystal and etch and get little pillars, then all of the crystals of the pillars are the same, but they have strain in them, and they're able to actually observe all of these kinds of effects. And this is the real data here. These are the models of what's going on in the explanation. So you can get both a coherent and incoherent strain going on. There's yet another technique that is quite useful. It has a different limit, where if we go back to our original formulas, where if I have these are whatever is driving my field, I can actually break out my averages as into the average of the square and the square of the average. Multiply this out, you'll get two kinds of terms when you multiply across, and that gets multiplied from this thing. And so the reason this is important is if I have the locations of my objects are not correlated, this term goes to zero. So what I need to think about here is if I have in a solution, I have a whole bunch of say identical objects, but they're suspended in a solution, and then the locations of those objects are completely random. And so my correlation term will go to zero, and only the original term goes forward. In that limit, my scattering basically comes n times the scattering of a single object. So that on the other hand, if I can only do this at small values of q. So the scattering there is basically the Fourier transform of the shape of the function. I can do that calculation for special cases. For example, in a sphere, I can just integrate from 0 to a instead of integrating over all space. You get a closed form solution. And this kind of small angle scattering is done by both Lois Pollock group and Saul Gruner's group. So some of you may have worked with them. If I take that complicated expression, and so I have my incident wave coming in here. This is my samples. Here's my exit wave coming out. I can calculate all the normal scattering geometries. But an important thing to consider is that at small angles, this is a very small angle here, q dot r is just q times r. But this angle here is going to be really small. If 2 theta is small, then this direction here is right along this direction. So I just make the approximation that this angle is that they're parallel. And that's the small angle scattering limit. That simplifies my calculations a lot. And so if I do it for some scattering cross-section area, I've simplified my vector form here. Here it comes out to this. This is now a one-dimensional integral. I can expand this rascal into a Fourier series. The first one is easy. The second one oscillates to 0. The third one gives me the square term here. So when I integrate all this together, this now looks like the first term's in expansion of a Gaussian. So I can expand my whole thing into a Gaussian, and whose size is the size of my object. And so my scattering cross-section ends up in this beautiful little Gaussian type of form for the small angle scattering. So if I compare, my Gaussian approximation is here in green. The original, the exact calculations for spheres in blue, and you can see it does a pretty good job. It's not perfect, but certainly in the small angle limit, I'm doing a pretty good job. It doesn't work quite right out here. I can go to the opposite limit where I want to work at large q. So, and in here, then I expand this thing. First multiply it out, and I'll get a 1 over q to the 6th out in front from the 1 over q squared. Right. And then I can expand on the these terms in here. Do I start breaking this part up and expanding the various parts, as I start seeing the different terms here, the parts which are left here oscillate away to 0, so I can ignore those. And then looking at, think of this, because Q is actually a large thing now, this term will dominate over that, and I get a 1 over Q to the 4th behavior. Okay, take all of that together. I guess the simplest way to see this behavior is if it's small q, sine of q is just q. So I get a q over q cubed is a 1 over q squared. Squared is a q to the 4th. Everything else is a higher order in q. This is the lowest order of things. This is called Perot's law. And so I can then, my small angle scattering, I can either get the size of my object in the far field, or I can get the size of my object in the field in the two different approximations. And that's the basis of small angle X-ray scattering, then used for all kinds of studies of protein folding and unfolding. It's commonly used now. So the biological small angle scattering community is huge at this point. Also, a lot of work in the polymer community, getting radius of gyration and so on. Okay. This is then related to another very powerful technique called the pair distribution function technique. Okay. And it relies on a very simple observation that our scattering cross-section generically look like the Fourier transform in the density function. But for a homogeneous sample, it doesn't matter where I put the origin of the universe. So when I do my integration, I can say I'm going to set this one object to be at 0, then I'll integrate over r prime. And I can do another one, r prime. So I get my scattering cross-section looks like a series of integrations where if I assume there's a particle at the origin, then r is just the separation between the two, right? At this distance up here. So if r is equal to 0, it comes through here. Right? And what we see is this object, and for homogeneous samples, looks like the Fourier transform of this thing. But this is just the probability that if I know I started at one object, and then I move a distance r, that's the probability of finding a particle at distance r from any other particle. It's known as the pair correlation function or the pair distribution function. So in practice, as we measure, the way you get this thing is you measure all the scattering over an enormous volume of reciprocal space, and then Fourier transform that back to get the pair distribution function. It works really well both for powdered samples and for single crystal systems. It's a little harder if you don't have either a good powder or a single crystal. One of the reasons that we like it at CHESS is that this technique requires high energy X-rays. So you need large Q values, because you're going to do a Fourier transform. So if you want to know what happens at small distances, you need to have large Qs. So in practice, we need energy, X-ray energies well over 20 kilovolts. People like to work out 30, 40, 50, 80 kilovolts to do a good job with the local structure. And over the past 15 or 20 years, there have been many, many examples, beautiful experiments. And currently the QM2 beamline at CHESS is really optimized for these types of measurements. And the basic idea is that you need to get all that diffuse scattering between all of the Bragg peaks. Okay? And so having incredibly high dynamic range to be able to really understand the details of the weak scattering at large Q values is really important. So this idea, though, can be extended to all kinds of surfaces and shapes. And so I'd like to take advantage. In my last example, actually show an example of a set of experiments that my group did actually some time ago now, using very similar ideas to study the growth of layer by layer growth of a semiconductor, of a complex oxide film, and give you some of the ideas of how subtle the details are that you can actually acquire from this. So let's see, I mean, there's lots of reasons for studying these complex oxide films, that they have really amazing properties, from superconductivity to ferromagnetism, You can have tunable dielectrics, wide band gap semiconductors, colossal magnetoresistance, you name it, it's all in there. The other really appealing feature about them is shown over here on the left, is that using molecular beam epitaxy or other growth techniques, pulse laser deposition, you can actually create atomically perfect samples. So the other day I mentioned that there aren't very many examples of this, but silicon being the primary one. But it turns out the complex oxides are a second example. In the research context, pulse laser deposition is one of the growth techniques that's actually able to do this. So the basic idea of pulse laser deposition is deceptively simple. You start with a substrate here. So whatever I want to grow my thin film on, and I usually have that sitting on a heater so that I get good diffusion when stuff lands. And then have a target. This is the material I want to deposit. So this could either be a powder or a single crystal, doesn't matter. And then I have an Excimer laser over here. So I take a high intensity laser pulse, comes in and attacks the target. It ejects a plume of material from the target, which then flies to the substrate, right, and sticks here. And that's how I transfer material from the target to the substrate. If I do it carefully, I can get really high quality samples. In our experiment, of course, we use the synchrotron to generate X-rays, and we monitor the growth of the substrate or the thin film while we're growing in real time. And so this is quite a challenging experiment, but it gave us tremendous insight into what's going on. A couple details here of the Excimer laser. The important thing is that we got about one pulse every 5 seconds. So that as you click, you wait a little, click, another, and so on. The plume, you need to know is that lasts for several tens of microseconds, but it does, it actually keeps the stoichiometric transfer. So whatever I had here, the stoichiometry lands here. So that's the ideal case, but it's very close to reality. For our substrate, we use strontium titanate, to prepare a high quality sample and so on. You have to do a lot of work in vacuum, but we actually, for these experiments, because it's an oxide, we had a base pressure of oxygen of about 200 millitorr. We did this experiment here at Chess several years ago in the old G line, working on a wiggler, not an undulator. But we had a lot of photons coming in. Okay, so here's a picture of what the experiment itself actually is. We were growing the substrate with strontium titanate. It's a perovskite structure, and we actually knew a lot about this material. To start with, I talked about a little bit yesterday in terms of electrochemistry. You can think of it as strontium oxide layers and titanium dioxide layers, and they just get stacked up. You combine really nice crystals of strontium titanate, and 100 terminated. Here's a start is an atomic force microscope image of our sample, and what you can see is it has a slight miscut to it. These are single unit cell high steps across these surfaces, and so you can see they're separated by 100 nanometers or so, and the surface cup is about 5 angstroms, half a nanometer. Here's our kinematic scattering theory. This is the same formula I showed you before, Fourier transform the densities. Okay? And so what I do is apply this formula to the following system, where I have a substrate, which consists of a stack of layers of strontium titanate, and then I'm going to grow a new layer on top. And so we've already talked about the crystal truncation rod theory and so on, and we're going to do that kind of an analysis here. With one slight simplification, I'm going to look at my surface layer, this yellow layer, and I'm going to break the density of that surface layer and parallels the component in the surface into 2 parts. One will be the average density of that layer, and the next will be the fluctuations in the density as I move around in it. So both can be functions of time. But only one, this is a homogeneous part, the average doesn't have any position dependence. All the position dependence fits in this piece over on the right. And then I just add up my scattering. So first in my scattering amplitude, there will be a couple simple parts. One is just the substrate. So I imagine I have a perfect crystal substrate, it has a scattering amplitude, and this is the truncation of the surface, which gives me my crystal truncation rod. Then I need to add to that my thin film that I've grown. So that layer has its own scattering amplitude. If it's homoepitaxy, this F is the same as this F. If not, it will be different. So it depends on if I'm growing europium titanate on strontium titanate, I get a different F. If I'm growing strontium titanate on strontium titanate, it's the same F. Then it depends on how many layers I've grown. In the simplest case, I just grow one. It's displaced some amount, there's a D space in here, and how many layers, it shows up in here. And then there's a coverage term here. So it depends on my coverage as a function of time, it will change. Right? And this is how I'm going to grow my film inside my equation, that the coverage of various layers will grow in time. This is the Bragg part, the coherent part. And then I add a diffuse part, which is the same part we just talked about for thermal diffuse scattering. So on, but here, due to the fluctuations, are the same idea. So I split rho into two parts. Rho bar is up here, and the fluctuations are down here. But now I only have an integral over my perpendicular components of R. So if I look at that and put this all together, I have what do I expect to see? And so over here, I've plotted, this is the specular reflectivity of the strontium titanate substrate. So I have this is my Bragg peak sitting out at the 001 position. And then in between, I've got the crystal truncation rod coming through. So if I just sit at this point here, this is the half integer spot. This turns out to where I have the maximum sensitivity to interference between the two layers. So what we're gonna do is over time, I'm gonna grow the coverage, add layer by layer by layer, and just grow them up, get thicker and thicker. And we'll be able to watch it grow on the crystal truncation rod. But in real time, we're actually going to watch the intensity at this point here. We'll plot it down here as a function of time. Let me see if I can. Where's my? Well, axis was running before. Here it is. Okay, there it goes. So you should see now as it grows, we get up in the top of the plot, we're seeing more and more wiggles as we get more and more layers. And in the bottom plot, what you're watching is the value of that intensity grow as the different layers come on. So I'll run this again in a second. But what you see up here are now we see all these little fringes. These are the fringes. This is the sine squared nx over sine squared x. These are all my intensity fringes. This is the thickness of my thin film. So I can just measure that. In this particular case, I've chosen to plot lanthanum strontium manganate as the overlayer. And what you see as it grows, instead of oscillating up and down, you can see that different layers are different. And if this had been strontium titanate on strontium titanate, all of these things would be the same height. So there's both the interference between the top and the bottom of my thin film and the roughness oscillations are going on here. So I can track both things at the same time. So let's see, I have to. It's hard to get out of. I'll run it one more time. So we started with a flat screen. You can see the layers coming in, and every other time there's either a pop, and if you look at the top one, One oscillation, it's on top, and the other oscillation, it's on the bottom. You can see that below. Okay, so that's a simulation. So, and that assumed very smooth growth. Pulse laser deposition, we don't have smooth growth. You actually come in with a pulse that lasts a few microseconds, but then they come only about one pulse every 5 seconds. And so we actually expect to see something like this, where as we start with high intensity and a first pulse makes the surface rougher, 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 about half coverage, it starts to fill in and come up. But if I wait, every time I give a little pulse, then it can anneal. The stuff diffuses around on the surface. So as I drop down, I don't see any recovery, but coming up, I expect to see some kind of a behavior here or a rounding. That's an artist's conception. Here's what some real data looks like. Right? So this is strontium titanate on strontium titanate, and you see the reflectivity drop pulse by pulse. And see, these are microsecond pulses that generate this, but they're many seconds wide. And so you see it stair-stepping down, but then as we put it on, it takes it a little while. It roughens and then comes up, roughens and then comes up, roughens and then comes up as we pulse it. And it doesn't quite recover back to 1. Okay, so that was a pretty nice one. There are various growth modes that you can actually grow a film in. And there are, the one we were just talking about is layer by layer, where you kind of grow one layer and it oscillates up and down and you count the layers. That's one possible growth mode. Another one is you could just imagine, as I put material on, it zips right over to a step. And so that step just flows across the surface. And so my reflectivity never changes. I just see a flat thing. It gets longer and longer and longer, but I don't see any of these roughness-induced oscillations. Another case is where I might not get flat growth. I might grow islands and get a really rough surface. And then the intensity will just decay in time. In the rural world, we get all of these going on and we try and optimize things and so on. So you can only get layer by layer growth in some systems in certain regions. This is really nice for growing these precisely controlled samples. Step flow growth is really nice also for creating very smooth samples. But these experiments are going to work in layer by layer growth mode. We can see for the particular experiments is that there's not a lot of temperature dependence. We're able to keep the layer by layer growth growing for quite a while over a wide range of temperatures. And if we do the experiment, you can actually now see, see if I got a picture of where this came from. I thought I had a photo of the experimental setup. Okay, I'll come back to this in a minute. What you're looking at here, this is the specular reflectivity, where at one point on the rod, so if you go across the rod this way, that's what you see. This direction is time. So we're sitting at one value of Q on the rod, and you're looking sideways. And so what you can see is on the rod, there's some oscillations here in the intensity. That's what you would have been seeing down here. This is at one point. But on the side and out of phase, with this, you start to see diffuse scattering. There's big, and then it's small. And it's big, and then it's small. It's big, and then it's small. And that this oscillation is out of phase with the brightness. It is brightest, so the specular oscillation is brightest when the diffuse intensity is weakest, and vice versa. So what you're seeing is the scattering move from the specular to the diffuse to the specular to the diffuse. So that was really nice. You can use it to solve crystal structures and so on the specular. But we actually wanted to look at what's actually going on in the nucleation and growth process. So we return to that diffuse scattering we were just looking at. And so here's a picture of what's going on, two AFM pictures. If I start with a flat surface shown in the upper left hand, and then I grow several layers of strontium titanate and look at it again, what I see is I still have the stair-step structure, but on each layer, I see all these little islands. So this is what we're starting to think of as the layer by layer growth mode, right? It's that the material didn't just go to the steps and have the step move across, that we nucleated islands on the steps, which then coalesce and create a new flat step and goes through, and that's why you see these oscillations. So what I can do, I take my AFM image and take the Fourier transform, I should get something which is similar to the diffuse scattering. And so what this is a digital Fourier transform of this image. And what you see is this sort of ring of scattering. And then if you say, okay, if I was doing an X-ray experiment, where would I be looking? And the way we set it up was to look in this particular direction. So this box here is more or less what we saw in the X-ray experiment. So if I study that and just plot the intensity coming across here, I see something that looks like this. So as I come in Q, I see a little lobe up to the specular, come down, and another lobe. Okay, just from my atomic force microscope. So qualitatively, that's also what I'm seeing in the X-ray. Okay, but then what you immediately recognize is the separation between islands is now something like 2 pi over the peak location. But this is the most probable distance. The reason we have a ring is because there's a well-defined average distance between objects down there in the surface. So here's the way our experiment actually worked. This is the figure I thought I had earlier, sorry. So I come in, I've got my sample down here, which has steps on it and islands. And my X-ray comes in at some finite angle, comes out at another angle. I'll have an area detector out here. So as I move up and down here, this is my specular truncation rod. In this case, we had to put an attenuator there so that we didn't damage the detector. And we put a mask over it, so so I'm just looking at one value of the reflectivity. And if I look at my data then I see a picture which looks very much like the Fourier transform atomic force microscope image I just showed you, where I get a nice diffuse peak and a central peak on the inside. And again, now the size, the separation between my objects is given by 2 pi over that Q value. So then we can do lots of things with this. We can actually model it if I assume on very general grounds that these are all little hockey puck shaped islands and so on. I can do a very simple calculation and you find that you expect the intensity of these diffuse peaks to have this particular form here, where this is, the name of this is a Lorentzian, which is this shape here to the 3/2 power. And it's a standard line shape, which basically that 3/2 power is just because it's random and in 2 dimensions. A very generic result. And if you fit the data to that form, put in the specular and add that thing, you get this nice red line here. So this line shape actually describes the data exceptionally well. And it's so if you think of a randomly placed island, randomly placed hockey pucks, that's the basic model that we've got here. It works incredibly well. This for the history buffs out there, Dubai was the first person to come up with this formula, and that's really a classic idea. Okay, so here's a blow up of one of those where I can see now the x-axis here is time, the y-axis is transverse momentum transfer, and then the color is the intensity. Okay? And so as we grow, we can actually see the diffuse scattering thing. Not only does it turn on and off, but it also moves. So the center of mass up here is at a larger Q than down here. So that there's not only are we getting intensity changes, that we're changing the Q values, which suggests that the size of objects and so on is changing. There's a couple different versions of what's going on there. And in this particular case, we're actually even able to see high order oscillations coming through a little bit. So now it's actually hard to show the thing, but here we actually fit each frame each time to a Lorentzian function. So over here is the data, and over here is the fit. So you can see we can model the data really quite well here. This basically is this picture. It looks like this picture, and now we have an analytic form that we can use as to go forward with. And the reason we want to do that is, remember we talked about this pair distribution function idea, and that we can do that same calculation for the two-dimensional surface as of ideas. And so this is an example of that. And so now what I've got here, let me explain the plot to you. I'm going to have a pair distribution function now, but this is my island distribution function. So the probability that if I had an island at position 0, what's the probability I have more stuff farther out? Actually, if I have material at 0, that I have more material. This direction is time. So we're going through a single oscillation. And so what happens is up here, it's small distances, but you see that what happened here is that initially there are no islands. And so if I have a little bit of material, the probability of finding material anywhere is very small. Well, as I move out to half coverage, what happens is this is basically telling me the size of my island. Okay, so if I start at position 0, at half coverage, as I move out, there's a high probability of finding material nearby until I hit some characteristic size out here. There, about, say 25 in these units. I think these are nanometers here. There, and then suddenly the probability that I'm going to find an island is relatively small. And I don't know if you can see it in the display, but what happens is it goes from bright, there's some really dark blue here, but then it gets brighter again out here. So this is the location of the first island. This is the size of the island, and this is the location of the next island coming back. So there's actually a little peak in here, and you'll be able to see it in the PDFs and so on if you change the contrast on your screen and so on. So this is actually, we've now been able to actually image the way the islands behave. And so they're over here, this goes away because there are no islands out here or here. And you can see this, also something interesting happens here, right? These are fluctuations. And so here the island is growing, we're adding material to it. The island doesn't really shrink. What happens is on this side, what we're really looking at are holes, little island, little hockey puck shaped holes. Here we have hockey puck shaped islands. This is hockey puck shaped holes. And there's a funny inversion as you go through the middle here. So that in one sense, the island just grows together, and over here the defect or holes. And what's happening now is the little lakes or little holes in the ground are getting smaller and smaller. So it's a really kind of a funny picture, but it gives a really nice idea about how big is the object, how far apart are the object, this in as a function of time going forward. And that's where I'm going to quit today. Okay, so let me turn this camera back on again. So are there questions, things I can answer today? Now, this is a lot of stuff today.
Well, is there any questions? While they ask questions, I'm going to write down again my email. So if anybody needs the presentations, please, if you're not in my contact group, just write me an email so I can send you the information. Joel, that was quite interesting because we had a view of like the backstage work, like all the math and thoughtful work to generate the X-rays and the experiments that some of us, we just do a little piece, and there's a lot of things that can be done at CHES that you show us today, all those applications.
And I think, exactly, I'd like to encourage people to think about, the Lois Pollock's group and Saul Gruner's group and Nozomi Endo are really experts at the small angle X-ray scattering. We have people who are really experts like Matt Miller's group in the structural materials and the strain analysis. We have Brunya's group is really expert in the electrochemical techniques. And this is just the scattering part. Right? Then you have Ken and Chris and Louise with the spectroscopy. It's just a whole nother part we haven't had a chance to, and they've had other groups. So I think that's part of my goal here, is just that there's this whole world of things, and each one seems really specialized, but in their own place, it's simple and straightforward. And like this last one, you can come up with a picture at the end, which is really, really powerful. As long as you don't go too far, right? It only talks about a little bit, but it told us a lot about how we were growing that material. And in the end, it looked pretty simple. Like I can come up with a really simple picture. And so I just think, encourage the students to, when you think about your problem, then come talk to us and see which technique is for you.
Yeah, it's impressive actually how all these mathematics can come and fit the data so perfectly. I mean, I'm really impressed by that. I mean, comparing the real data with the fitted data and all the information you can get out of it.
I think that's also from a scattering point of view, the good thing that X-rays are really good at is taking averages over a large number of particles. So if you think of powder diffraction, we can get really good structural determinations and lattice constants over large numbers of crystals, and you get averages and so on. And so you can get the average properties of things really, really precisely. The electron microscope, like with David Muller and Lena Krokotis, right? They come in with an angstrom beam and they tell you what's going on at that spot. So if you want to look at a defect or a point, that's what the electron microscope is really good at. And so together, the X-rays are giving you what is the ensemble average, which you care about for things like chemistry. But if you want to know the details of what's inside your ensemble, you got to kind of pull it apart, and that's where the electron microscope works. So I think that using both, using the right tool for the right thing is appropriate. I mean, people get into trouble. There's always a harder way to do the experiment, but you don't get any points for doing it the hard way. You get the points for doing it and getting the right answer. And so I think that it's as much as I love X-ray techniques, people also need to use Raman electrons and so on. And so the X-ray people do their best to do things with X-rays, but there's many cases where you should be using a different probe.
So have Brunya done this work in Operando to look at nucleation at an electrode surface?
We would like to.
Okay.
It's a long time ago, Tito and I looked at under potential electrodeposition.
Yeah. That's what I was thinking on.
Yeah, and so, but you really need a system that's well behaved to do this, right? And so I think our dream, right, is to do the quality experiment we did in the pulse laser deposition on electrochemical deposition, or just to actually watch it happen. But it's been a challenge, and we're getting closer and closer. I don't know if Tito and I live long enough, we might do it. So we're going to need long life and good health.
That's good.
But the tools are getting better and better, right? It's and I think we're getting pieces of it, right? But some of the new, something I didn't talk at all about was imaging. Some of the work, I think the work that Xin Wang has been doing, like with the lithium batteries and so on. Looking at the dendrites and things. And so those are, we need to sort of get all of this going at the same time, right? But like maybe some of these students will be the ones that actually do it, right?
Yeah, that's right. Yeah.
But it's lots of careful work. So I think next week, Professor Brunia is going to talk about electrochemistry, right?
Yes.
Maybe I should send him a note and have him talk about under potential deposition. And
Yeah, that would be good, yeah.
Yeah, mostly he'll do spectroscopy, but he'll do some structural stuff, I'm sure. But we should twist his arm a little bit to make a link here.
Yeah, we are gonna announce Brunia's also. He wants to announce his presentation. So,
Yeah,
so I might send it to the PREM community.
Yeah.
So,
yeah. And I recommend this course. I've taken several electrochemistry courses from Professor Brunia, and this is the short version. It's kind of through a fire hose, but it's not. He has a semester-long version, and then he has this one is 4 or 5 lectures. This is sort of the short and sweet highlight version, and so I have to keep going back every couple of years because I keep forgetting my electrochemistry. So I'm going to try and sit in on his lectures next week. And it's just fun listening to him too.
Yes, he's gonna. I'm gonna be sending. He's doing an invitation because he has quite a group that he invited. So I'm gonna be sending a new link possibly for those lectures. They're gonna be again next week, Monday to Thursday, and the following week is gonna be X-ray spectroscopy for surface analysis with Dr. Cabrera. So we expect to have you here and enjoy all those talks.
Yeah. This is I'm looking forward to all these talks.
Yeah, I think it's a great thing, a great opportunity that we have due to the COVID-19 emergency to have these talks that we wouldn't have them if we were like hands-on experiments on the lab.
Yeah, no,
the positive things from something
I'm
that
really
is not
sorry people can't do the hands-on experiments because I'm a big fan of those. But this is the best we can do right now, and it's just different.
Yeah, but I think after these talks that you explained so much math that has to be done to get the information we want and everything, I think they will appreciate even more the results when they got them actually in the hands-on experiments.
And also, I think we're not expecting you to be an expert after this. This is just to almost let you know it exists, right? And now you check with me or with any of the scientists. They can direct you to most people need one of these slides, right, for their experiment, not all of them. But it just exists, and there's a lot of math there which simplifies in the end. And so people like Dubai did it and explained it, right? And so now the rest of us that aren't really great mathematicians, we can just use that and move forward and really analyze our data. And you can tell, does this model describe it or not? And so I never really know I have the perfect model, but I'm really good at eliminating models. I have a long list of models which don't describe the data, right? And then eventually you get more and more confident in that your model is okay.
Yes, that's the process to go through. Well, I'm going to be sending today's PDF as soon as we finish this meeting. So thank you all for joining us during this week, and I hope to see you back next week then.
Thank you, Joel.
Thank you, Joel.
Okay. Bye-bye.